Welcome to this essential training video on aligning business problems with machine learning, or ML, goals. Machine learning is often used in modern applications, ranging from finding friends on social media to medical treatment. Successfully applying ML requires much more than just picking an algorithm. You must ensure your solution addresses a real need. We will explore the critical steps needed to correctly frame a business challenge as a solvable ML problem. Understanding this foundational alignment is key to ensuring your ML project delivers real value and avoids solving the wrong problem. Let's begin our journey by understanding why business goals must lead the way in any ML project. This entire process is often iterative, meaning we constantly circle back to improve and refine our steps. Before you even think about code or data, you must understand the overarching goal. Machine learning is a powerful tool, but the algorithm itself is only a small part of a solution. The most fundamental reason your ML project exists is to solve a business problem, whether that is detecting fraudulent transactions or making product recommendations. Therefore, your entire ML system must be primarily driven by clear business objectives. Companies measure success by tangible business metrics, such as increasing user engagement, reducing costs, or speeding up processes. They do not care about internal ML metrics, like improving accuracy from 94% to 94.2%. Unless that improvement translates into real business value. If you focus too much on complicated technical scores without demonstrating business impact, your project might be killed prematurely, wasting time and resources. Always keep the big picture in mind. The algorithms and methods are just one part of a greater process. What did we learn here? We learned that every ML project must start with a defined business objective to ensure the work is meaningful and focused on delivering quantifiable results that matter to the organization. The important point is that ML metrics are meaningless without corresponding business value. This diagram illustrates the necessary flow. We start with the business problem. We then ask if an ML system is genuinely required. If yes, we proceed to define ML objectives, which leads to measuring the final business impact. If the impact is high, the project is a success. If the pattern is simple, we should use a non-ML solution instead, as we will discuss in the next slide. The arrows show that the process is sequential and goal-oriented. Understanding this high-level structure ensures that resources are allocated only when ML is truly the appropriate tool. The initial scoping, or project planning phase, is crucial for laying out the goals, objectives, and constraints. This entire structure ensures that all technical work eventually maps back to a quantifiable outcome for the business. This systematic approach prevents teams from getting lost in unnecessary technical complexity, when simpler solutions would suffice. The success of the system depends on integrating all components, starting with clearly defined business requirements. We must translate the initial business request into concrete ML goals. Once you have your general business objective, the next critical step is assessing whether machine learning is actually the necessary or cost-effective tool. ML shines when it needs to identify complex patterns from input data to automate a decision-making process. For example, determining a rental price based on dozens of characteristics is complex. However, if the pattern is simple and easily defined by a clear rule, such as using a lookup table to find a state based on a known zip code, ML is not the optimal choice. Non-ML solutions are often the best starting point, giving you a baseline to evaluate more complex ML solutions against. Therefore, you must rigorously ask yourself, what is the best way to phrase my question as a machine learning problem? We want to ensure we are addressing the right task. What did we learn here? The key lesson is that ML should only be used if the problem involves complex patterns that cannot be solved by simpler traditional software solutions. We must always strive to use the simplest method that solves the problem effectively. This diagram highlights the decision point for using ML. We start with the input data. We check if the pattern is simple and easily defined. If yes, we use a simple lookup table or a fixed rule, which results in a non-ML solution. This is generally faster and cheaper. If the pattern is complex and hard to manually specify, like predicting a stock price or assessing fraud risk, then we proceed with an ML solution for prediction. This process ensures that ML is only applied where its core strength-learning complex, non-obvious patterns is needed. For a successful ML system, framing the problem correctly is paramount. If the pattern is simple, such as using a zip code to determine a state, ML is unnecessary. We reserve the computational intensity of ML for complex problems that traditional software cannot easily solve. This iterative thinking helps guide the project development early on. A business problem, such as speed up customer service, is not an ML problem until it is structured properly. To be solvable, an ML problem needs three key components: clear inputs, specific outputs, and an objective function. The objective function is mathematically critical, as it guides the model during its training phase. Think of the objective function as the ruler the model uses to judge its own performance, measuring the loss or error caused by wrong predictions. For instance, if your goal is to predict house prices, the objective function calculates how far off your prediction is from the actual price. The model's entire training goal is to minimize this calculated loss. This step formally links the fuzzy business objective like maximizing user engagement to a precise, measurable goal the machine can optimize, like minimizing a specific loss metric. What did we learn here? We learned that translating a business need into a mathematical objective function is the core step in aligning business and ML goals, allowing the machine to quantify and minimize prediction errors. This ensures the model learns what is truly important for the business context. This diagram visualizes the funneling process from a high-level business goal down to a measurable objective function. The starting point is a broad business goal, such as increasing user retention. This is translated into a more specific ML objective, like improving recommendation relevance. This objective dictates the ML task, for example, running an item classification or ranking model. Finally, this leads to defining the objective function, such as minimizing log loss, which is a metric the model can directly optimize during training. This systematic reduction ensures that all computational effort is directed towards supporting the initial business outcome. This alignment of goals is necessary because ML systems must satisfy specified objectives. The objective function acts as the central guide for the learning process. Without this clear translation, the model might optimize for something useless or irrelevant to the business. After defining the guiding objective, you must clearly define the model's expected outputs. The type of output fundamentally dictates whether your ML task is classification or regression. This choice is crucial because different algorithms are better suited for different task types. If the outcome you are predicting is a fixed category or label, such as predicting whether an email is spam or not spam, then you are dealing with a classification problem. If the outcome is a continuous numerical value, such as predicting the exact selling price of a car or the temperature tomorrow, then you are dealing with a regression problem. Getting this distinction right early on determines which algorithms and evaluation metrics you should use later. This framing step ensures the ML algorithm can proceed effectively. What did we learn here? The most important takeaway is that the type of output you need determines the fundamental machine learning task type, either predicting a discrete category, classification, or a continuous number, regression. This flowchart visualizes how defining the required output determines the ML task type. We start by framing the problem, which leads to defining the output type. This output must be either a discrete category or a continuous value. A discrete category leads to a classification task, while a continuous value leads to a regression task. Both outcomes lead to the next step, which is model selection, and defining the appropriate evaluation metrics, such as accuracy for classification or mean absolute error for regression. The core process of framing involves defining inputs, outputs, and the objective function. This determination is vital because it sets the technical path for the entire project. Classification is one of the most common and successful types of supervised learning. In classification, the goal is always to predict a discrete category, often referred to as a label. For example, in the business world, classifying an incoming support message as a complaint or an inquiry is a classification task. Classification is broken down into subtypes. Binary classification involves exactly two outcomes. For instance, classifying an email as spam or not spam. In this scenario, one class is designated the positive class for the purpose of the study. Multi-class classification is used when there are more than two potential outcomes, such as identifying a website's language from a predefined list of possibilities. Crucially, in classification, there is no continuity between the output categories. A flower is either a setosa or a versicolor, not something in between. What did we learn here? We learned that classification predicts a specific, fixed label or category, and that the count of these labels determines if it is a binary or multi-class problem. This diagram displays the hierarchy of classification tasks. Starting from the general classification task, we branch out to binary classification, multi-class classification, and multi-label classification. Binary classification, as seen in the spam detection example, has two outcomes. Multi-class handles problems where we select one option from 3 or more choices, such as species identification. Multi-label classification, which is a related but slightly more complex task, handles cases where a single input can have multiple categories simultaneously, though we won't focus on that now. The key point is that classification deals exclusively with discrete, non-continuous outputs. This defines how we frame the ML problem's output. If your business problem requires predicting an outcome that is a number, such as a dollar amount, a quantity, or a measurement, you are dealing with a regression task. Regression falls under supervised learning, where the model learns from examples of input features and known continuous outputs. Unlike classification, where the output is distinct and separate like male or female, regression deals with continuity. For example, predicting the number of bike rentals per hour is a regression task, because the count can be any positive integer, and there is a continuous relationship in the data over time. This makes regression suitable for forecasting and time series predictions, such as anticipating stock price movements. Understanding regression is essential for problems where calculating a degree or magnitude of change is necessary. What did we learn here? Regression predicts a continuous numeric value, distinguishing it from classification's discrete categories. This is appropriate when the variable varies smoothly over a scale. This structure shows the fundamental flow of a regression task, where an input feature, or features, are processed by a regression ML model to produce a continuous output Y. We draw this intuition from simple datasets often used to illustrate regression, like the wave dataset, which plots a single input feature against a continuous target variable. The outcome, the predicted target, can theoretically be any value within the defined range, emphasizing its continuous nature. This approach is distinctly different from the discrete outcomes seen in classification, where the result is a fixed label. By setting up the problem as regression, we prepare to use algorithms designed to model numerical relationships, such as linear regression or decision tree regressors. To feed data into your chosen ML model, whether it's for classification or regression, the data must be organized into a format the computer can process. This usually means organizing data into a table format, where each row is an instance or sample, and the columns represent the features. Features are the properties describing that instance, such as a customer's age, gender, or purchase history. Crucially, the quality of your prediction is entirely dependent on the quality and relevance of the features you provide. If you want to predict a patient's gender but only provide their last name, the model will fail because the necessary information is missing. The work of crafting and refining these inputs is known as feature engineering, and it often has a bigger influence on model performance than the exact algorithm chosen. What did we learn here? We learned that inputs must be represented as descriptive features, and that successful ML hinges on providing rich and relevant features that contain the information needed to solve the problem. This entity relationship diagram shows how the initial business alignment flows into data preparation. The business_problem maps to the ML_goal, which determines the specific ML_task, whether that is regression or classification. The ML_task requires the data_input. The data input itself is structured, consisting of rows, samples, and columns, features. Successful alignment means ensuring the features collected possess the feature_relevance necessary to achieve the ML goal. Feature engineering is the continuous effort to ensure this connection is strong, as features are the properties describing the entities the model must learn about. The input data acts as the knowledge base from which the model extracts patterns. The final, continuous step in alignment is measuring success, which means knowing if your model generalizes accurately to new, unseen data. We use evaluation metrics, such as accuracy for classification tasks, or mean absolute error for regression tasks, to quantify this success. Critically, blindly applying an algorithm without understanding its underlying assumptions and how it interacts with the data will rarely produce an accurate model. Therefore, success must be defined by clear metrics that directly relate back to the original business question asked in slide 2. For example, if the business goal was fraud detection, a high recall metric might be more valuable than pure accuracy. This ensures that the ML system is not only running correctly, which is reliability, but that its predictions are actually useful and interact well with other parts of the system, which is maintainability and adaptability. What did we learn here? The crucial point is that measuring success is vital to the iterative process. Metrics must be chosen carefully to reflect successful generalization and alignment with the initial business objective, ensuring the entire system is working correctly. This diagram illustrates the alignment feedback loop, bringing the full process into a continuous cycle. The cycle begins with the business objective, translated into the ML goal or loss function. Training the ML model leads to predictions on test data, which are measured using evaluation metrics. Based on these results, we determine if the success criteria are met. If successful, we proceed to deployment. If not, we must loop back to the business objective, which might mean refining the goal, adjusting the data, or changing the model. This feedback mechanism is essential for adaptability and maintainability in production systems. The ability to accurately measure success determines if the entire solution is providing value to the organization. This systematic check ensures that we continuously solve the right problem.